Okay, so first topic, just to go over quickly, is surface integrals of vector fields. So like integrating two forms or just like the surface integrals. So what does this mean? So if you want to compute the surface integral of f over s, so we have f dot ds. Oh, sorry. That's the same as doing f dot nd sigma. So here, ds, the notation for ds is the same as nd sigma, that notation. And in the two-form language, you would write that our double integral of f dot ds is going to be the integral of the one form f, one form sub f. Okay, and so what is the idea that we're going to be doing? You have some surface, and first thing, no matter what, you always do is parameterize. Like for most of the questions we've done, you always parameterize first. So we parameterize, and given some parameterization, we can find d capital S, which is going to be doing the derivatives of our parameterization, cross-producting them, and then the variable, the other variable. So that's how you define d capital S. And when you do the integral, what are you going to do? You're going to plug in your parameterization into f, and then multiply it by d capital S, which is our cross. In the one form language, you can say that you're going to have some two form, and you're going to do the double integral of the two form. Again, you plug in your parameterization. So that's what the RUV is. And then because we're in like two form language here, what does a two form do? A two form eats two vectors. So you have a two form eating two vectors, it spits out a scalar. So then you could do the double integral of some scalar. And this notation in like forms language, if you don't like it, this notation is the same thing. I think this one is more like the videos, where he has, again, this is the two form. You're still plugging in the parameterization into your two form, but instead of this like parentheses thing, you can just compute the Jacobian or the derivative matrix. Because the derivative matrix is going to have two columns. The first column is the same as your partial with respect to the first variable. The second column is going to be this partial. And so this notation is the same as this notation for form language. Any questions about the definition? Okay, so let's do an example then. Okay, so this is recitation question 154, and says, we want to compute the flux of the vector field given like this out of the triangular planar region with vertices 1, 0, 0, which I call P, 0, 1, 0, which is Q, and 0, 0, 1, which I call R. And we're using the direction away from the origin perpendicular to the surface as the direction of positive flux, meaning like your flux is like moving out of the page, or yeah, it's perpendicular. Okay, so we have this question. The first thing we always want to do, no matter what, is we're going to have to parameterize something. So there's 3-step process. First, we want to parameterize our surface so that we can find ds. Second step, we rewrite our function as, I'm going to do it in the forms language. So rewrite f as two form. And then third, we follow the formula. Okay. So yes.
So is this the method that's not Gauss's theorem?
Yeah, this is not Gauss's theorem yet.
But this is like another way of doing these questions other than Gauss's theorem.
Yes. So this is like the parameterization way. So like we're saying in vector language, right? Wait, sorry. This is like we're not following Gauss's theorem because Gauss's theorem requires a like closed 3D shape. We're using, for this question, we're going to use this definition, which is more like integrating a two form. So this is what integrating a two form means. Okay, does anyone have any ideas on how we should parameterize this plane, this triangle? So like, how do you, if you are given some plane, you want to first find the equation of the plane. And how do we find an equation of the plane? We need two things. Anyone have ideas on what two things we need for the equation of a plane? Yes. Yep, exactly. So we need to find a normal vector and we need to use a point so that we can write the equation of a plane. So right now I have 3 points, P, R, Q. So if I just take two vectors, for example, PR and then PQ, and I cross product these two vectors, that gives me another vector that's going to be normal to our plane, because that's what the cross product does. So if I find this PR, so PR is going to be the R point minus the P point, which gives me -1, 0, 1. PQ, doing the same thing, gives me -1, 1, 0. And so if I take the cross product of that, I see that my normal vector is 1, 1, 1. Now, what is the equation of a plane? Well, we need the normal vector dotted with xyz minus the point. And this point, we could choose any of these points. It doesn't matter. You could choose P or Q or R. I just chose P because it looks the nicest, like 1, 0, 0. So then you have this normal vector dot with x minus 1, y minus 0, which is y, z minus 0 is still z. When we do the dot product, we have x minus 1 plus y plus z. And so if I simplify it, this is the equation of my plane, this flat triangle. So now that I have my equation of the plane, though, I still need to parameterize it. Like, this is in implicit form. This equation is implicit. So we need to parameterize it, meaning we want to get rid of a variable. Right now we have x, y, and z. Let's get rid of one of the variables. So if I get rid of z, what would happen? Well, this parameterization of the plane, you still have x, you still have y, but now I want to rewrite z. So if I rewrite z from this plane, I get z equals 1 minus x minus y. So now our parameterization just has two variables. And this exactly describes our whole entire plane. This is what a parameterization is. Any questions on how I got this parameterization? Yes. Yes, and also because like dealing with things in 3 dimensions with 3 variables is harder. It's like parameterizing, we want to get rid of one of the variables. Okay, so now we have our parameterization G, and what else do we need in our formula? We're going to need the Jacobian matrix or the derivative. So if I take the derivative of G, so this first column is going to be the partials with respect to x. So I have 1, 0, -1, 1, 0, -1. Partial with respect to y gives me 0, 1, and -1. So now I have my parameterization, I have my derivative matrix. Okay, second step is that we needed to rewrite our fields as a 2 form because we're going to follow the form definition of the formula. So what does I correspond to? In the 2 form, the canonical 2 form formula, I represents the dy dz. J represents the dz dx. K represents the dx dy. So I can rewrite my form as I keep all the like variables the same, 3y dz dy dz minus 2x dz dx plus 2z dx dy. And so this is now my 2 form. And so now we can follow the formula. So we have our 2 form, we have our parameterization with the derivative. What does the formula say? We want our 2 form to have our parameterization. So I rewrote, yeah.
I just have a question about the fact that we have the vector field as two form.
Yes.
And I just like wait, like up there.
Mhm.
Yeah. So I was just trying to remember, like like the derivative in one form and two form derivative. But how does in like the vector language, how does it change? Like if you take the derivative of vector field, is it just another vector field?
So we don't define the derivative of a vector field, but we do define like the curl of a vector field or the divergence of a vector field. So it's like the summary I had at the end of last chapter, where we define so like you don't take derivatives of vector fields. We take derivatives of one form. It's like this derivative, like the analog in vector language would be the gradient here, or the curl.
So how are you? Oh, I guess because it'll be a two form is like equivalent to the curl, which is another vector field. Then you can take a vector field and put it into its form.
Yes.
Okay.
Yep. Okay, so so now we follow the formula. So we have our 2 form. I will plug in my parameterization. Y is still y according to our parameterization. So why don't I copy my parameterization so you guys can see in red. X is still X in my parameterization, but Z I define differently. Z I define as 1 minus X minus Y. And then I have my 2 derivative matrix. And so what does this, like, how do we do this? So from last week, there's a method where you can either make a big 3x3 matrix and do the determinant of it, or we can look at each term individually. So we have 3y. What is dy dz? We take the y row and then the z row, and that gives us a determinant. So we do the determinant of that. Because remember, dy wedge dz, that's the projected area in the yz plane. So it makes sense that we have a 2x2 matrix and we're taking the determinant of it. Then we have minus 2x dz dx. That will be, so dz, put our first 0 here, and then dx. So that's our x row. And then we do the same for plus 2 times this 1 minus x minus y. Dx dy is our first 2 rows, the determinant of that. And so we can evaluate these and simplify and take the integrals of them. Would anyone like me to explain the integration from continuing? Yes?
I just have a question. The y boundaries, why is it 0 to 1 or 1 minus x to 0 rather than 0 to 1?
Yes. Okay. So the x bound we know has to be 0 to 0 to 1 because that's just x. But y has to be different because if y can go up to 1, then what if x is also 1? You get that the z like term is -1, but we were told that z can only be between 0 and 1. Everything here is between 0, 1, 0, 1, 0, 1. So we need this last coordinate to be between 0 and 1 also. So I set the last coordinate equal to 0 and simplify to get y equals 1 minus x. And so that ends up being our upper bound. Then I also set this last coordinate equal to 1, and I simplify to get y equals -x. But what can x be? X can be between 0 and 1. So our smallest number is 0. And you can check that this makes sense because x at most can be 1. So you get a 0 here. That's fine. But x can at least be 0. So then you get the correct bounds of 0 to 1. If x is 0. Yes.
When you set up what the term is, the same term is dz of dx.
So dz dx is like the canonical version of how we write a two form. Like a two form is always some like some term dy dz plus some other term dz dx plus some other term dx dy. So in our equation, if we had like dx wedge dz, specifically for this example, it would say like plus 2x dx dz. And so then you would have plus 2x dx, you would have the x row at the top and the 0 at the bottom. And they give you the same result anyway. Okay, any questions? So yeah, you can finish the integration and get a half. Any questions on this problem? Okay, so this is for the flux. We had the direction away from the origin is in the direction of positive flux. So we do this whole question normally. What about this next question? So we have similar shape, but now it tells us that we're using the direction into the surface as the direction of positive flux, meaning that our normals are pointing inwards instead of outwards. Usually if it says like outward pointing normals, then you just do the problem normally. Here, because it's in the opposite direction, it turns out that you can do this problem just like you did the last problem, compute the flux, but then your final answer will be the negative of it because we've switched orientation. How do I know that we have to switch orientation? So let's work it out a little bit. So I write my vector field as a two form. We always need to do that. What do I also always need to do? I need to parameterize my surface. So if we first look at, yeah, we can first look at this surface. So think of this like object as two surfaces. You have the like circular part, like the cup part, and then you have the lid part, the flat part. So it's this surface and this surface together that gives our whole shape. So if we look at the like cap part of our shape, then how do we parameterize it? It tells us that our paraboloid is y equals x squared plus z squared. So why don't we need to get rid of a variable. Why don't I get rid of y? Because they already tell you what y is. So our parameterization is in terms of x and z. X and z are still the same, but y is x squared plus z squared. Yep.
So like right here, what you're doing is you're like parameterizing and then putting it, it's like a flux 1-2 form, and then integrating that flux to find the flux.
Yes.
But in this question, would it be possible for you to also use Gauss's theorem to close boundary?
Let me think. I believe yes. Yes. And actually, if we were to use Gauss's theorem, what do you think this would give us? So if we wanted to use Gauss's theorem, we'd be doing the divergence of f, which would be 1 minus 1, which is 0. So actually even if you're doing some integral, whatever, it still gives you 0.
And the answer is 0.
Yep.
So it's just like way quicker.
Okay. So let's continue with just the two form though. So we have this cap right now. And so what I'm going to do, I parameterized it, I found a derivative. We need to follow our formula. And so let me just say that we have our two form, we do all the math, and we get negative pi. But why did we end up getting negative pi? So here's a little bit of intuition. When we have our two form, and we have our two form is y dz wedge dx minus z dx wedge dy. In this two form, dz dx is telling you projected area in the zx plane. Okay, So if we compute that derivative or determinant, sorry, the area is going to be -1 according to our dz dx. So I get -1. But what variable is not here in the z and x? We don't have a y. Doing this tells us that if we go in the positive y direction, then the flux is going to be -1. So going in the positive y direction this way, our flux is -1. But the question said that our flux, like positive flux, is pointing inward. So if we were going in the positive y direction, our flux should be positive, not negative. So it turns out that instead of doing the z wedge dx being -1, we're going to make it be 1 instead. So we flipped a negative sign. We made it negative because it was in the wrong orientation. Let me explain the green one. So the green one is the same idea. We have dx wedge dy. What variable is not here? Z is not here. So if we go in the increasing z direction, based on our red arrows here, if we're going in the increasing z direction, we should get a positive number for this wedge. Do we get a positive number for this wedge? Well, let's see. We get 2z. How do we know if it's positive or negative? Well, when z is, wait, positive z direction. Oh, sorry. Okay. Yeah, in the positive z direction, z, because we have like 2 arrows in different sides, we have to look at z above 0. When z is positive, we want the normals or the flux normals to be negative. When z is in the bottom half, we want the arrows to be up, positive. So the wedge is giving us 2z, which means that if z is a positive number here, our flux will be positive. But we don't want it to be positive. We want it to be negative. Now, if z is negative in the bottom half, we want the flux to be positive, but our formula, our expression would tell us that we have a negative number. So everything's flipped. We want everything to be negative instead. So instead of having this wedge with UV, we're gonna want it to be negative of it. So we're gonna want -2z instead as our like determinant. So like thinking about this intuition, that's why at the very end, if we did it the normal way, that's fine. And then at the very end, just take a negative sign of it. Yes.
Wait, I was like at blue all stars, and it's like the right hand rule, like
Oh yeah. There's also the right hand rule.
how do we use that in the
So like if you have this shape, and you're going, so the right hand rule is that you want your fingers to curl in the direction that your curve is moving. So like wait, let me think. So if we're going counterclockwise, our fingers should curl this way according to our curve. If we're going counterclockwise, our fingers should curl this way according to the counterclockwise, and our thumb points in the direction of positive flux. So this normal would give me positive flux. And that's how I know if my arrow is pointing inwards, we're backwards. We're in the opposite orientation. So like, because we're going counterclockwise, so my finger curls this way, and this should be my outward normal. Does that make sense? For the right hand rule. So the right hand rule tells you which direction should be the positive normal vector. Because this. Any questions on that?
tells you which direction should be the
Positive normal. Yeah, flux. Okay. So for this example, we did the flux of this cap part and we got -pi. If we do the flux of this green flat part, our lid, we end up getting +pi. Or I said it backwards. We got pi for the cap and -pi for the lid. So the overall flux is going to be you add these two things because we our whole entire solid, and we end up getting 0. Yeah, any questions on this problem? Okay, so then let's do Stokes' theorem now. Okay, so Stokes' theorem, we can recall what a curl is. So I just rewrote the definition of curl from a few weeks ago. And so what is Stokes' theorem saying? So Stokes' theorem says that if we want to compute f dot dr over some curve, instead we can do the double integral of the curl of f dot ds. And remember that ds is equal to n d sigma. In one form language, you would have this integral over a boundary. This notation with the partial thing, this means boundary. So we're going to do the boundary of the one form that equals the integral of our actual surface or actual like shape of the derivative of our one form. Yes.
What's the difference between this and that same thing that's written on Gauss's theorem or whatever? Like in the one form language?
This?
Yeah.
Wait, did I write the same? This is a one form, whereas in Gauss you have a two form.
Okay, so in Gauss, we take the derivative of two form over the actual
Like shape, yeah.
and it's
Mhm. Okay, and so let's see some. Okay, and to note that the Green's theorem. So Green's theorem we did last week. That's like if you had a flat surface, right? So it turns out that Green's theorem is a special case of Stokes' theorem. Specifically, Stokes is for like 3D shapes. Green's theorem is once you have 2D shapes. So like Green's is the 2D version of Stokes' theorem. So let's do an example to see this. Okay. We want to compute the circulation of f dot dr, where f is given as this vector field, and c is the boundary of our hemisphere. So we have a whole sphere, we cut it in half, we just have the hemisphere, and c is going to be that like curve of the hemisphere. Okay, if we use the cap of, so we have our hemisphere. We can either take our surface as the cap, so the top part, because the cap, the surface or the boundary of the cap is still like the outer part of our hemisphere. So the boundary of the cap is still this purple thing. Or we could choose our surface as the bottom circle. Because if you just have a circle, the boundary of that is still also the curve. So you want to make sure that whatever boundary you choose should be some curve. Okay, and it doesn't matter which surface you choose, but you'll see that choosing the green surface will actually be much easier. So let's actually do the green surface. So I'm choosing our circle, our flat circle, and our boundary is the purple thing. And we want to compute the circulation. Yeah.
I don't know if I'm forgetting something, but when we did grades like last week, when did we parameterize and get like DS or anything? We didn't really do that, did we? Just kind of took the derivative of that one and that one. It's kind of like the
Right. So in 2 dimensions, this. So if you think about the flat circle, right, in our hemisphere, what is the normal vector of the circle of the flat circle? Like a normal vector, any normal vector.
Yeah.
Would be the k hat, right?
Okay.
Like the normal, I put it downwards, but okay, let me make it upwards. Our normal is 0, 0, 1. So if you were in 2D, this n would be 0, 0, 1. And how do you get d sigma? The formula for d sigma is let's have our parameterization be called S. SR cross S theta, dr d theta. And so the parameterization of this circle, say our circle is x squared plus y squared equals 4. Then our parameterization of the circle would be S of r theta will be r cosine theta, r sine theta. If we take the cross product of this, we'd end up getting r. So the formula n d sigma tells us we would be doing 0, 0, 0 with r dr d theta, because r dr d theta is what we get according to this, what d sigma is. But r dr d theta, that's in polar coordinates. So if we converted, if we converted that to regular coordinates, r dr d theta is what, dA. So that's how in Green's theorem, that's why we only have like a dx dy. Yep. And also a trick, if you notice, last week I said Green's theorem in 2 dimensions, you only have the k component of the curl, right? And now that makes even more sense because what is Stokes' theorem saying? We're going to do the curl of f dot 0, 0, 1 dr dr d theta. So you would have something here, question mark, something here for the curl, and some number here for the curl. When you do that dot product, well, these cancel out because you have something times 0 plus something times 0 plus you would just have this number times 1 dA. So that's why in this definition for Green's theorem, you have like sigma, or sorry, derivative of nx minus m y, something like that. I forget the definition, but that's like the k component of the curl, ln dA. That's why Stokes' theorem in 2D gives you Green's theorem. Any questions on that? That was a little bit of derivation. Okay, so let's continue our example then. Okay, so we have our cap and we want to follow the formula. So what do? Let's use the cap. Parameterize the cap. So what is that? Did I say cap or lid? Lid, parameterize the lid, the flat lid, which is a circle of radius 3. So we have a circle of radius 3. Well, we're on a flat plane, the XY plane. So Z is 0 no matter what. So in my parameterization, I don't even have to think about Z. Z is 0. And then I can keep X and Y as is. Then I need to find a derivative matrix, which is 1, 0, 0, 0, 1, 0. And the point of this is that we're parameterizing so that we can find what is D capital S. So if I take the cross product of our columns, I end up getting 0, 0, 1. And so ds will be 0, 0, 1 dx dy, which you also kind of just saw in the derivation. Okay, then we need to find the curl. So how do we find the curl? To find the curl, what's the formula for curl? You don't have to memorize the formula. You could just do a determinant of, you write ijk, the partials, and you write what are your terms in your function. So our function was y negative x0. So I put y negative x0, and I compute this determinant. So it gives me that my curl is going to be -2 in the k component. So I'm left with something in the k component only. So this is my curl. So I have my curl, I have my ds, and now I can follow the formula. The formula says that we want to do the curl dot ds. So the curl was 0, 0, -2. ds we found as 0, 0, 1 dx dy. Doing this dot product, I get -2 dx dy. What do we, if I take out this -2, I get -2 times the double integral of dx dy. We know that double integral of, there's like an implicit 1 here, dx dy. What is that? instead of actually calculating a double integral, what could I do instead? Like what does this integral, yes. Yes, exactly, area. And if I had just a triple integral dx, dy, dz, yes, yes, exactly. So don't forget about these rules. Yep.
Yeah, so this is basically Green's theorem, is it not?
Mhm.
So my confusion is like, if we parameterize and we are able to do it in two variables, then we can just use Green's theorem.
Mhm.
Where does like the actual Stokes theorem come in? I mean, like, are we parameterizing on every Stokes theorem question?
So Stokes theorem is an equality. So if we're doing the one way, like it might work. We're doing this is in the other. So like let me like in 2D, if it's in 2D, like I guess you don't have to use Stokes, you just use Green's. Like it's where Stokes is coming in is that Green's theorem is actually Stokes theorem.
Right, but like, so when it's like like you have that curve surface dichotomy thing on your graph on that table you showed, is that just like 2D versus 3D? And if so, when it's a 3D question and you're using Stokes to calculate the circulation or whatever, do we always parameterize and then follow suit with like that Green's theorem we've learned? Because if you parameterize it to 2D and then you're basically doing Green's, which is Stokes, or is there ever a situation where you're kind of like, do you ever not parameterize and then use Stokes to its full capacity where you have a full curl? You know what I'm saying?
Well, you'll have a full curl if you're in 3D.
But we just were in 3D and we parameterize so it's in 2D, and then we can with the cake component of the curl. Right?
Yes. So Stokes theorem. Okay, I guess where we're also using Stokes theorem is that Stokes theorem says it doesn't matter which surface you choose as long as the boundary is the same. So if I had chosen this top cap, then you can't do a Green's theorem, right? Because it's not flat.
Okay, so you wouldn't parameterize them?
You can still parameterize it and you would follow the formula, but it's like now you have
But if you parameterize only in two variables, right?
yes.
So then you can use Green's
theorem. Okay. So even though you're parameterizing it to two variables, that doesn't necessarily mean it's 2D. Like your surface has to be flat for it to be considered 2D.
Okay.
It doesn't matter about the because for all the parameterizations, we're moving it to either two variables or one variable, right? So the idea is that your surface should be flat in 2D in order to use Green's theorem.
Okay. So then anytime we're doing, like, we're asked to find a circulation or whatever, or use Stokes theorem, our first step will always be to parameterize
Yes. Okay. I would say yes. Okay, so let's see. Oh yeah, so yeah. So you continue and get 2 times the area of a surface. Our surface was that circle. So area of a circle is pi r squared, where our radius was 3, and so we end up getting negative 18 pi. Any more questions on this problem? Okay, let's take a 5-minute break. So come back at 2:38.